Good morning to all of you. My name is Dheeraj Kumar. My paper ID 497 and title of my paper is Induction Motor Drive for Low Cost EV with Improved Performance using a 3-level VSC. Before starting my presentation, on behalf of all the authors, I want to thanks to organizing committee for selecting our paper for this conference. Content: Introduction, Experimental Setup, RTI Model for VYF Control, Experimental Finding, Conclusion, References. Introduction: The electric vehicle EV are becoming popular choice to meet the challenges of global warming and air pollution. Every electric vehicle is tested under certain driving cycle. There are 29 driving cycles reported which are acquired using supervised learning methods. The extra urban driving cycle EUDC is one among them which reflects the aggressive behavior of EV and has high speed driving methods. The induction motor IM has high efficiency at higher speed, easy control and natural de-excitation during inverter failure. The GM EV1, Tesla Roadster and Tesla Model S are few examples of EV which are used induction motor. A VYF control is the simplest control scheme for IM drive which can be implemented in open loop and closed loop both. The open loop VYF control scheme for index IM is reported using LabVIEW through FPGA in 6 and closed loop presented using integrated development environment and built through Arduino in 7 and using Xilinx through WebCT in 8. The open loop and closed loop VYF control scheme for induction motor is implemented using only MATLAB Simulink in 9. The work reported in 689 used two-level inverters to operate the induction motor, resulting in only 3 levels in line voltage. The induction motor drive operated with a 3-level inverter has 5 levels in line voltage. The 3Li fed induction motor drive has the capability to decrease the voltage levels to 3 with decreases in speed by half. Due to this, switch stress of the VSC decreases during decreases in the speed by half of the induction motor drive. A cost comparison reported in 10, the overall cost of 3Li is lesser than 2Li. This paper presents the hardware implementation of the VYF control scheme for an induction motor operated with cascaded HV CHV 3-level inverter. The applicability of this induction motor drive for EV is tested with the EUDC. Experimental setup. This setup is divided into 3 sections. First is the control section, in which sense speed of induction motor through tacho generator and generated switch signal through D space CLP1104 for each single phase VSC for power section. In power section, second section, in this section, constant amplitude of source voltage is converted to variable amplitude through 3-phase variac and fed to the each single phase VSC through 3-phase isolation transformer. Third is the excitation section. The field of DC electric generator is excited using diode bridge rectifier. Here in right side actual photograph of a laboratory setup is seen. Real-time interface RTI model of VYF control. This one is divided into 4 sections. First is the reference speed section, second is the modulating signal generator, third is the sense speed section, and fourth is the switching signal generator. Here the sample time is 100 microsecond. Experiment Experimental finding under EUDC. In this figure, channel 1 show waveform of line voltage supplied to induction motor. Channel 2 and channel 3 show the waveform of phase A and phase B of a current drawn by induction motor. And channel 4 show the waveform of speed of induction motor. From channel 1, it is observed that line voltage has two wave shapes, first and second, that is 3 levels and 5 level wave. From channel 2 and channel 3 waveform, it is observed that phase current are within range during complete EUDC. And from channel 4 waveform, it is observed that speed has follow the pattern of EUDC. Experimental finding during the first transient state. During the first transient state, it is so that line voltage is a 3 level, 1, 2 and 3. During the second transient state, line voltage is still in 3 level, first, second and third. During the third transient state, line voltage is still in 3 level. During the fourth transient state, line voltage is changed from 3 level to 5 level, first, second, third, fourth and fifth. During the fifth transient state, it is so that line voltage is only 5 level, first, second, third, fourth and fifth. During the sixth transient state, line voltage again change from 5 level to 3 level. Experimental finding power quality analyzer. Power quality analyzer results has been recorded at the terminal of induction motor at a different speed. First is the rated speed, that is 100%, 1410 rpm. Second is the 75% of speed, that is 1055 rpm. Third is the 50% of rated speed, that is a 705 rpm. From 1410 rpm to 705 rpm, that is speed, as speed decreases, line voltage here we can see change from 5 level to 3 level. And here we can observe that the THD of voltage also decreases. And during the whole transient state, we maintain the load current almost constant. Conclusion: the V-bias control induction motor drive successfully implemented on an induction motor drive experimental hardware setup using DSpace CLP1104 real-time controller and MATLAB Simulink. This induction motor drive operated with a cascaded H-bridge 3-level inverter and tested on EUDC. Results of this VYF controlled induction motor drive demonstrate successfully tracking of EUDC speed pattern and improve power quality. The use of CHB 3-level inverter induction motor drive is able to operate effectively in complete speed and power range and reduce switch stress and control complexity of the system. References: there are the sum of the important references which helped in successful completion of this work. Thank you for your attention.